So Professor Subramaniam has been in the editorial board of Journal of Atomization Spray and International Journal of Spray and Combustion Dynamics. He's a well-known figure in the area of theory, modeling, and simulation of multiphase flow, turbulence, reacting flows, and such. And he's also the founding director of the Center of Multiphase Flow Research and Education, which I think one of the kind of center in the world. So with that, I would request Professor Subramaniam to please start your talk.
Thank you so much, Himanshu. Let me try to share my screen here. Are you able to see my slides at this point? Okay, thank you. So thanks very much to you and to Anubhav and to Mahesh Panchagnala and the whole organizing team at IIT Madras for inviting me to, it's a great honor to speak on Bala's 60th birthday with the celebration. So I thought I would start with a few reminiscences of Bala. I also thought I would put together some photographs I found from the internet. So Bala, when you search Balachandar, you show up, of course, as you're famous, but there is also a famous Veena player, Balachandar, who shows up. And I thought with your interest in music, you might like to know that you share your name with a famous Veena exponent. So Bala, of course, we've had a very enjoyable collaboration over all these years. His intellectual contributions are legendary. His scientific approach, one could talk for the whole talk on that. And he's made many contributions, technical and otherwise encouraging junior researchers. And I really think, his accomplishments are definitely worthy of honor of a distinguished alumnus. Bala himself, when I talked to him about this on his birthday, he said there are three important things in life: good food, good company, and good science. So I completely agree with Bala, and I thought I would share with you all a verse on good company. And this verse is not in English. English is a relatively young language for those of us who come from India. And it is in a language called Sanskrit. And this is actually a language that predates many in the world. So let me tell you the verse and then the translation will show up. So it goes, Jadyam dhiyo harati, sinchati vachi satyam, manonnatim dishati papam apakaroti, chetah prasadayati dikshu tanoti kirtim, satsangatihi kathaya kimna karoti punsam. So this is, Bhartrhari is a great poet, Sanskrit poet. Around 400 in the Christian era he's dated. And this is from one of his verses, which says, it's about extolling the value of good company. What does good company do? It removes ignorance, sprinkles your speech with truth, uplifts one's sense of self, removes sin, delights the mind, spreads one's fame in all directions. And he says, tell me, what does good company not do for a person? So Bala, I'm thankful for your good company. So, with
Thank
that,
you,
I will move on to the talk. Which is a talk on a theory of multiphase turbulence. So let me start right away with pointing out some of the features of multiphase turbulence, particularly this multiscale feature. So in this cartoon, you're looking at three different images of some really fantastic experiments that were done in a fluidized bed at the National Energy Technology Lab by Schaeffer and Gopalan. And what they were able to do is image particles all the way from the microscale, which is about 1 to 10 particle diameters you see on the left, to the mesoscale, where you may have clustering on the order of 100 particle diameters, and then to the whole extent of this riser, which is about 22 meters. So the key learning that we've had over all these years is that particle scale physics actually do impact device scale quantities of interest. And this broad division of scales, we can identify many interesting features. At the microscale, you have velocity fluctuations in the fluid and in the particle. Kumaran talked a little bit about that in the first talk. There can also be drag and drag fluctuations in elastic collisions and a fluid-mediated particle-particle interaction, so shielding effects, which cause draft kissing and tumbling, etc. And these experiments also show us that shape and rotation are very important at that microscale. At the mesoscale, what happens is particles organize in structures And the real challenge in multiphase flows is how to capture this interaction of the organized particle structures with the fluid. When you get to the macro scale, of course, you have particle wall interaction, and then the device geometry influences the flow a lot. So I'm going to try and focus and see whether we can do something better from a theoretical standpoint in capturing this interaction of the organized particle structures with the fluid. So as I noted, this multi-scale interaction results in particles organizing in either clusters, or sometimes it's called preferential concentration in a different regime. But fundamentally, both these are characterized by fluctuations in the number of particles or the particle volume in a region. So the theory that we would like to develop should broadly be applicable to both these phenomena. So we've seen preferential concentration for many years typically in homogeneous isotropic turbulence through simulations, but also experiments. And here, intrinsic turbulence is dominant. So the fluid phase turbulence is dominant. Particles are getting convected around depending on their Stokes number. They organize in these regions, typically high strain rate. They get flung out. The maxi centrifuge mechanism is typically implicated in seeing these kind of structures. So you're looking here at particles in a turbulent duct flow by the work of Banco and Esmaili. And there's a comparison here between experiments and DNS. But the real problem that I'm interested in is clustering in a different regime where you have significantly denser particles. They're loaded, that is, the volume fraction is higher. And here we are looking at two different situations. And here what happens is the wakes generated by the particles cause something called pseudoturbulence. In fact, the particles themselves can induce turbulence. So we're looking here at experiments again from that Schaefer experiment images. And then you're looking at simulations by Jesse Capisulatro, who's going to speak after this. Very beautiful volume filtered Euler-Lagrange simulations that show very realistic images of clustering. But this is also seen in another situation, which is called homogeneously cooling gas-solid flow, which is work done by Christine Hrenya and Xiaolong Yin, where again they show that these clusters form. Now the difference between the CIT and the HCGSF is that in CIT we have a mean slip between the fluid and the particles, whereas in this other case it is just pure particle fluctuation velocity that's initializing the problem. But nevertheless, the physics is different in all of these, and Christine Hrenya has a very nice annual review of fluid mechanics paper where she elucidates the various mechanisms, but there is still not a convincing theory that predicts all of this. So with that in mind, I'm going to jump into a little bit of basic terminology so that I get everyone on the same page here. We're going to do averaging operations, and they will be represented by these angle brackets. So Q is any quantity, it could be a particle or a fluid. And when I say averaging, I'm going to mean mathematical expectation. So there is a notion of an event space, and a realization is denoted omega, and that sets in that event space have a probability associated with them. And so that's the definition of the average. Now, under appropriate conditions, this average can be estimated by ensemble averaging, or if it's a statistically homogeneous flow like the HCGSF, you could do volume averaging. Or in a time averaged, in a statistically stationary flow, you can do time averaging. And if ergodicity holds, then all these should converge to the same quantity. Okay? Now, we can describe these multiphase flows in two ways. One is what we call a random field-based approach, or a stochastic point process-based approach. We call them field-based or point-based. More conventionally, the field-based is known as an Euler-Euler or a two-fluid approach, interpenetrating continua, etc. Whereas the other one is called an Euler-Lagrange or a kinetic theory-based approach. So if we look at the representation, so in the very basic sense, we can think of an indicator function for the particles, which is depends on every realization, and one for the fluid. That would give us the most fundamental elements of the random field approach. Of course, you then have velocity and pressure, etc. And in the stochastic point process approach, we have positions of and velocities of particles. And again, that's on every realization omega. And so they will change depending on the realization. Now, what do I mean by single point? When I say single point, I'm going to do an averaging of this and of the indicator functions here of the particles, and I get the average solid volume fraction. Now, the same thing can be done for one particle. And then if we do that, then you get what's called the number density, where you average over the summation of particle delta functions, which is a Klemontovich type approach. So this would be called a Klemontovich fine grain densities being averaged. We can also do 2-point statistics, which are very important. So I will call them CPP, for instance, in the field-based, where I take the indicator function of a particle at the position x1 and another one at x2, and then I look for their joint information and do the ensemble average. And similarly, we can have a 2-particle counterpart for the point process based. So the bottom line is we know that these are actually, we can go between these two representations. Very nice work by Torquato and others shows that for homogeneous isotropic fields with monodispersed particles, we can actually have exact relationships going from C to rho, etc. But what I'm really interested today is focusing on the Euler-Euler based. So we will not be talking that much about the point process. Just be aware that one can go from this to the other. And so device scale simulations, like I showed you, that span the entire device, they really need tractable single point closures. We really cannot afford to do 6-dimensional simulations for the kind of industrial problems where these answers are needed. So I'll emphasize that we really want to stay at the single point level, and that's the whole goal of this talk. So let's look a little bit more about how do I represent clusters in a mathematical sense, taking the CIT as an example. So for instance, you can see here that if I situate myself at a point X in space, I look at another point X plus R, which is situated at a separation vector R, then I need to know what is the joint probability of finding particles simultaneously so that I can characterize clusters. So it's interesting that the presence of clusters does not show up in the average solid volume fraction. So I can have 2 flows with the same average solid volume fraction, one clustered and one unclustered, as is shown at initial time here and at later time. This is a very, very fundamental point. And so it basically means that in a single point theory, I cannot represent clustering. Its signature is found in the 2-point particle covariance function as shown here, but it does not show up in the single point limit. In fact, if you take the limit as separation goes to 0 of this guy, you'll get back the average volume fraction. And so this is the big problem. Fluctuations in number and particle volume do not show up in single point theories, but to do device scale simulations, we need single point models and closures. So what we've learned so far is to kind of introduction to the challenges. Turbulent multiphase flows are intrinsically multiscale phenomena. They result in this kind of clustering and preferential concentration. Single point theory is desirable for ease of modeling, unclosed terms, simulation, etc. But 2-point statistics are needed to characterize fluctuations in particle and fluid volume fraction. So this makes the treatment, the theoretical treatment of multiphase turbulence uniquely challenging, and it's not been satisfactorily addressed by previous statistical theories based on random, these Euler-Euler methods. So if you look at Drew, 1983, Collins, 99, Sundaresan, 2008, Fox, 2014, they don't really address this satisfactorily. So let's go back and look at the origin of where these theories come from. So if you look at single phase turbulence, you go to a random field theory. The resulting theory in multiphase flows is the 2-fluid theory, which Drew proposed in 1983. And it basically deals with a mean solid volume fraction, a mean velocity of the fluid phase, mean velocity of the particle phase, mean pressure in the fluid phase, and a mean pressure in the particle phase. And then you derive evolution equations for these things. And then the difficulty there fundamentally was this calculation of mean pressure in the particle phase, because particle collisions result in a pressure, and those are not well represented at that single point level. So this was one of the difficulties in Drew's closure models. In 1967, actually, Anderson and Jackson, much before Drew, proposed a 2-fluid theory where they did filtering operations in random fields. Unfortunately, Anderson and Jackson thought they were deriving an averaged equation, but nevertheless, their volume averaging approach was really a filtering. That was later clarified rigorously and very nicely by Capicolato and Desjardins in 2013, where they derived the volume filtered Euler-Lagrange method. So what does filtering do? We take a particle field as shown down here, you apply a filter, I've shown you a Gaussian filter with delta, and you get smoother fields basically, right? So you can keep increasing the filter width and you can smooth the fields out. So what filtering does when you do it to velocity or pressure, it generates another random field. So filtering a random field results in a random field. This is important to keep in mind, because when you write equations and write closure models, you have to be careful whether you're modeling a random quantity or a deterministic quantity, as Drew was doing, right? So nevertheless, we'll find that filtering is a very, very powerful way to analyze multiscale phenomena. And it's not just numerically expedient, as VFEL shows, which has been remarkably successful, but it actually leads to a fundamentally new theory of multiphase turbulence. That's what I'm going to try and show today. And the key result I'm going to anticipate, I showed you that the single point limit of 2-point covariance does not show signatures of clustering. But what is interesting is that the single point limit of the 2-point covariance of the filtered field does. And this result is so absurdly simple that, when you see it, I was kicking myself why I didn't see it before. So let's walk through the result a little more carefully. So what I'm going to do is I take realizations of particles, and then I have, and this cartoon shows that I have several of them, I have an ensemble of them, and then I take expectation of this product, indicator function at x1 and x2, and then I form my CPP, which I've already described before, right? Now, what I do then is I take the field and I filter it. And when I filter it, I call this field phi bar, which is very straightforward. I take the indicator function, I hit it with the filter function, x minus y. We'll typically look at homogeneous filters with a given filter width. I have in mind mostly a Gaussian filter. Okay? So when I do that, I get these filtered fields. And then what I do is I take the ensemble of realizations, and then I do the filtering, and then I do the expectation. And now I call this CP bar P bar, which is filtered particle fields, right? So, and this is basically expectation of phi bar. Okay? So now what is interesting is, how is this covariance related to the covariance of the original unfiltered field? And in fact, it's quite trivial to show by taking expectation and expanding these definitions that in fact, what I get is, it is related to the original covariance with a double filter. Okay, it's a convolution. And what is interesting in the homogeneous cases, I can replace these x plus r's with just, I can remove the x, it's just a function of the radial separation distance between the pairs, between the 2 points, right? And so CP bar P bar is CPP with a double bar, where the double bar indicates this double filtering or a convolution. So covariance of the filtered volume fraction field is the doubly filtered covariance of the unfiltered field. This is an interesting result. What is more interesting is what happens in the limit r goes to 0. So when you take the single point limit of the covariance of the filtered volume fraction field, lo and behold, it's not the mean volume fraction. The single point limit of the covariance of the filtered field contains filtered 2-point information, which is what we wanted. So essentially, we are taking these separations y minus z, which are not at 0 at different points. We are hitting them with the filter. And so we're going to grab that information down into its single point limit. So this is the fundamental result. So as long as we are now careful in defining true fluctuations, this is the foundational part of the theory. Other definitions of fluctuations that have been used before were either non-random or they were not centered. That is, they don't have a 0 mean. So the correct way to define the true fluctuation is this quantity, phi check, which is the filtered minus the ensemble average of the filter. So this is, this will generate what we call a covariance function if we take the 2-point version of this. And we call that K P bar P bar. And its expected value of phi check, which is nothing but our CP bar P bar with the mean removed, with the products of the means removed. Now, what we'll find is the single point limit of this yields the filtered volume fraction variance, which is what we were after. So now if I set the limit y equals x in the evolution of that equation, I find a very nice equation that defines the filtered volume fraction variance. So you get a time unsteady term, mean flow convection. This looks very much like standard turbulence theory. You get triple correlations with this U check velocity, and then you get a production term, a transport of flux. Some new terms arise. One is this non-commutative flux, which arises because there is a difference between what is convecting with the mean flow and this mean U bar because of our filtering operation. And then there is a change of measure because the divergence of this UP bar is not 0. So these are, the particle velocity fields are not divergence free always when filtered and averaged. And then we get boundary terms because when you do filtering and you hit boundaries, you have to account for that effect. So what is interesting about this equation is it explicitly depends on the filter width. So I can do a multi-scale analysis. I can change the filter width and I can examine the flow at different scales. And it can be used to augment a standard mean and second moment equations for, say, filtered quantities in the particle and fluid phase. So you would add this on to a single point closure for the mean and second moment equations that are standard. Now, what is neat? What are the implications of this? So the first thing is my evolution equation for the filtered volume fraction covariance will contain a signature of clustering. That's to be expected. It's a 2-point quantity. What is interesting is its single point limit, which is the filtered volume fraction variance, also contains a signature of clustering, and whereas its unfiltered counterpart is actually agnostic of clustering. So that's the key result. So we can build models for single point closures, say for drag and heat transfer and gas solid flows with particle clustering that are functions of a single point metric of clustering, this filtered volume fraction variance. And now the question is, can the evolution equation for this filtered volume fraction covariance, the 2-point, help us gain a mechanistic understanding of clustering? So let's look at the 2-point piece, which is this phi check XY. When we do it in a homogeneous case, like for say CIT, we get purely a function of the separation. And I'm going to use Monin and Yaglom type notation and call this B phi check R. Okay. So we can derive the evolution equation of this B phi check R. And you will see that there are two terms here. One is a transport in separation space with these fluctuations in particle volume at the point in question, at its separation distance, and then the particle velocity. And so you get these two symmetric terms, and then you get another term which depends on the correlation between particle velocity fluctuations and particle volume fraction fluctuations. So this will inform how stuff varies in a homogeneous flow. This is actually very similar to the predecessor to the Kalman-Haworth equation into single phase turbulence. But unlike the Kalman-Haworth simplifications, our flow is not isotropic. And the velocity field is also not solenoidal. So we can't even use, say, Chandrasekhar's results for axisymmetric turbulence, which was a big disappointment, because otherwise we could simplify this to 2 or 3 functions and try to solve for that. But nevertheless, even with this equation, we can analyze, say, Jesse CIT data, and we're actually in the process of doing that. I also had the idea that we might be able to analyze some experimental data that Filippo Coletti has generated in this very nice falling particles experiment, where he's also able to observe clustering, and he's able to generate these what are called space-time autocorrelations. So what he's showing here is looking at the center of the duct, looking at a slice, he's able to show how velocities correlate. These are not really 2-point at the same time correlation, they're 2.2 time correlations, but still there is a hope that we could explain some of this data using this theory. And now I'd like to, in the last few minutes, give you a sort of landscape and chronology of multiphase theory and how all this came about. So I mentioned in 1967, Anderson and Jackson first started what they call volume averaging, which is really filtering. And this led to what we call two fluid simulations. Actually, in about 1991, I believe Shamlal, Madhav Shamlal, who was a student of Giraspov at the Illinois Institute of Technology, he developed the Amphix code. And these are what we call the two fluid simulations. At the same time, around 1983, prior to that, Drew developed his ensemble averaging two fluid theory. And I put this two fluid simulation under the average theories because they really use closure models that are averaged. They're not using stochastic closure models. And so those closure models came from a mesoscale description of a kinetic theory. And remember that in a kinetic theory, they're assuming binary instantaneous collisions. So it's a collision modeled approach. It's not a collision resolved approach. In about 1999, Sundaram and Collins wrote a very seminal paper in which they described the two-point theory for statistically homogeneous flows, where they really were able to analyze many of the things that I talked about, but they did not extend it to inhomogeneous flows. And it was fundamentally a two-point theory. Over the years, we've been in my group and several other groups like, Don Koch and more recently, a whole slew of researchers have been doing particle resolved DNS, which is a collision resolved approach to develop closures for drag pseudo turbulence that go into these ensemble average models. But one thing that was observed by Sundaresan, very key point, is he found that these two fluid simulations are actually difficult to resolve, meaning the more you resolve them, you unearth all kinds of mesoscale structures. Some of that could be numerics, some of that could be the mathematical nature of these equations. But nevertheless, he was one of the first with Agarwal to discover the mesoscale structures in these averaged equations. And then he developed a different approach where he started filtering the averaged equations. And that's a Sundaresan theory from 2008 and 2011, leading to filtered two fluid models. At this, and now chronologically going around 2012 is when I think Jesse and Olivia's paper came out, where they really kickstarted this volume averaging approach, recast it as a filtering approach, and developed VFEL with Lagrangian particles. About 2014, what Rodney Fox did was he took this mesoscale description as a starting point and developed a turbulence theory for multiphase flows using a sequential phase and Reynolds averaging. And more recently, what I did was showed that we can develop fluctuation hydrodynamics from filtered fields. And this leads to this, what I call a unified theory, which is really reconcilable at all scales, meaning this theory reconciles down to the DNS microscale, a collision resolve description, whereas the other theories do not. It's based on true fluctuations and it incorporates 2-point statistics. So why do I call this theory a unifying theory? It's because I can recover Sundaram and Collins's homogeneous 2-point theory as a special limiting case. If I set my filter to be a delta function, I just get their theory back. If I do the same thing in the single point limit, I can recover Drew's theory as a special limiting case. And I can also explain Sundaresan's coarse graining as something that misses some random fluctuations. So what happens is when we filter, the residual terms in our particle or fluid quantities can contain either random fluctuations or also some non-random unresolved fields. The true fluctuation actually captures the random fluctuations because it has the phi bar, the filtered minus the average filtered. Whereas when you do the filter of the average and subtract the average, then you don't get those random, you get a non-random fluctuation, which is really what Sundar was after, because he was trying to scale it up to very large devices. The difference between these two is what I call the difference between the filter and the average. This would be a seeming choice to build a theory on. It contains random fluctuations, but it's not centered. Its expectation is not zero. And that's why we need to use the true fluctuation. So only the true fluctuation satisfies the requirements of being both random and centered. So
Professor Subramaniam,
the other advantage of this theory is that—
Sorry to interrupt, Professor Subramaniam. Could you wrap up? It's almost time. Yeah, thank you.
Yes. So I think I will just close with saying that this obviates some needs for the sequential phase averaging and Reynolds averaging, and fully exploits the potential of Anderson-Jackson's volume averaging. And with that, I am almost at the end, which I think I will just skip through these. The challenge is, of course, using direct numerical simulations to capture these unclosed terms would require very large DNS, which resolve the clusters that we were seeing. And this also does not assume scale separation. So closure models are filter and filter width dependent, which is a little unfortunate, but at the same time, these are some of the common features for all the multiphase turbulence theories. So to close out, I think I will skip these slides. I just wanted to acknowledge Bala's sabbatical visit, where he started a question. I have a simple question for you. If you get a call like this from Bala, you know it's not a simple question because he has thought about it a lot. But anyway, it inspired me to start deriving these equations around 2016. And Jesse's collaboration, I'd like to acknowledge, from 2017, which helped me a lot in coming up with these ideas. So with that, I would like to just summarize and say that we have some new potential to analyze clustered systems and other systems with complex dynamics, and using this result. And so with that, thank you for your attention. Best wishes to Bala for more good food, good company, and good science. I'm happy to take questions.
Thank you, Professor Subramaniam, for an excellent talk. So now we have 2 minutes for a quick 1 or 2 questions.
Shankar, enjoyed the talk. Lots of information to digest. One question I have is that if you take a practical problem such as fluidized bed or other things, how much difference will there be when you deploy these different models and simulate them to highlight the differences between these different closure assumptions?
That's a very good question. So as I said, there's a lot of devil in the details. So when you take the theory, the accuracy of the closure models, the mathematical well-posedness of the equations themselves, which change when you change the closure models, the numerics, all these play a role, right? So I think it's an ambitious task to go about and conduct simulations based on 2 different theories and really show that the closure models. I think it's possible, but it's a long-term effort. it's definitely not something that we're going to see tomorrow. I'm more hopeful that when we look at homogeneous flows like Jesse's CIT data, that we can actually show something a little more, that's more data analysis and doing budgets of terms rather than closure models. So you're right about that. That is a long-term effort.
Right. So in the interest of time, we can move to the next speaker. Thank you, Professor Subramaniam.
There is a question somebody has asked, they're raising their hand.
Who is raising the hand?
So would the filter which traverse the microscale? Ah, yes. So Swagnik Ghosh has a question, would the filter which traverse microscale and the mesoscale? So that's a good point. So to build the right collisional closure model, you have to have the filter width larger than the domain where you can reasonably expect collisions, right? So then you get the right model for the particle pressure, just like Rodney did. And then beyond that, yes, you could increase. Yes, so you could traverse the filter width across the scales, exactly.
All right, so those who have more questions, please write to Professor Subramaniam. I'm sure that he'll get back to you.
Thank you.
All right. Thanks, Professor Shankar.